Tasha.
Hello, my name is Steven.
Hello, my name is Jiha.
Today we'll be talking about the seafloor mapping for geohazard assessment, specifically earthquakes.
Bathymetry data is essential for navigational safety and is used in a wide range of other applications. Bathymetric surveys allow us to determine the depth of a body of water as well as map its underwater features. Flood inundation, contour of streams and reservoirs, leakage, scour and stability, water quality studies, dam removal, biological and spill and storage and fill in reservoirs and ponds are all areas where bathymetric surveys are used. The vast majority of our oceans, on the other hand, remain uncharted, unexplored and undiscovered. Only a small area of the seafloor has been mapped using direct measurements. The remaining bathymetry is calculated using satellite altimeter data and only provides a rough estimate of the seafloor contour. A significant challenge in developing the precise seafloor surveillance infrastructure for earthquakes and tsunamis is discussing the architecture of observation locations for hypocenter determination accuracy of earthquakes, as well as environmental management for observatory devices on the bottom. The occurrence of events such as earthquakes, volcanic eruptions, submarine landslides, or other rapid processes capable of changing the morphology and character of the seafloor, such as gravity-driven sediment flows, fluid emissions, platform migration, progressive erosion at canyon heads, and so on. Marine researchers can keep track of minor earthquakes caused by the movement of tides in the deep ocean by placing data collecting ocean bottom seismometers. These little earthquakes are caused by the daily expansion and contraction of the seafloor caused by the tides. Placing seismometers on mid-ocean ridge where volcanoes build new seafloor and other seismically active portions of the seafloor will assist marine researchers to figure out whether parts of the planet are at danger of a huge earthquake in the near future by tracking how stressed these places get over time.
There is also a general lecture that revolves around our topic of interest, and the title is Subducted Bathymetric Features Linked to Variations in Earthquake Apparent Stress Along the Northern Japan Trench. It was written by Moyer P.A., Bilek S.L. and Phillips W.S. So a little bit about this general lecture. It stated that ocean floor bathymetric features such as seamounts and ridges are thought to influence earthquake rupture process when they enter the subduction zone by causing changes in frictional conditions along the megathrust between the subducting and overriding plates. Once subducted, these features have been described as localized areas of heterogeneous plate coupling.
The point one is about importance. Knowledge of bathymetry is important for a wide variety of users, starting with the fundamental understanding of geological and oceanographic processes affecting our planet. Early echo sounding profiles across Atlantic Ocean, for instance, enabled Bruce Heezen and Mary Tarp to understand the relationship between the mid-ocean ridges and earthquake seismicity, and played an important part in the recognition of one of the most significant paradigm shift in science, the development of hypothesis of seafloor spreading and plate tectonic, Hess 1962. Ocean mapping holds such an importance that it is just so synonymous with regular checkups that there are plenty of reasons why this is such an important issue. Firstly, the future of our planet and the well-being of everything living in it are linked to the health of our ocean, from the carbon that constructed us to the temperature we could survive in, and being the largest uncharted food bank for us humans. Deep diving into the fundamental and the inner workings of our planet is crucial as long as we want to remain as a tenant of this realm. As of the present time, data collected weren't enough, as errors like miscalculation could amount to a large effect on a larger scale. The Nippon Foundation GEBCO Seabed 2030 project is one of many organizations who have a vision of creating a perfect and complete global ocean map, which then allow the human race to understand the whole picture of ever-growing issues and effectively find a solution. We could increase our tenaciousness and resilience through our deep understanding of the ocean. Tide and surges, waves, and other coastal inundation could be a major threat to a huge volume of people. Both casualty and collateral damage would be inflicted on these events will effectively hurt our community and society. Only by having a complete understanding, efforts could be made into protecting our communities and be a deterrent for any possible reoccurrence.
There are several methods used in seafloor mapping for earthquake assessments, which the first one are repeated seafloor survey. And the accuracy of the system is persistently improving, and the utilization of autonomous and remotely operated devices for deep water study is increasing. All these techniques allow further identification of rapid seabed morphological changes at any depth with remarkable resolution. The difference between two co-registered digital elevation models obtained from repeated multi-beam echo sounder surveys is used to determine seafloor changes. The produced difference map shows elevation changes. Combining the difference in depth over the areas of interest produces the volumes associated with surface changes. Co-seismic seafloor displacement, volcanic eruptions, landslides, and their morphological evolutions, submarine deltas, canyons, and channel in fjords have all been detected and monitored using this method. The second method used was seafloor geodesy. Seafloor geodetic techniques without satellite links identify seafloor movement and the resulting minor changes in length and volume caused by tectonic forces, allowing for relative or absolute positioning. This data is supplied at the same high resolution level as satellite-based land approaches. Acoustics are used in seafloor geodesy to identify relative seafloor deformation or to transfer the position of the seafloor to the global reference frame, known as GPS acoustic or GPSA. This is accomplished by placing seabed nodes that can operate independently for up to 10 years. Active tectonic faults are shown by measuring millimeter-level displacement across tectonic lineaments. High-precision monitoring of potentially unstable volcano flanks or continental slopes is also possible with seafloor geodesy. The third method used is fiber optic technology. Telecommunication businesses primarily use fiber optic technology to deliver telephone signals, internet connectivity, and television signals. It is also used to detect light guides, imaging instruments, lasers, sonar, and hydrophones for seismic waves or earthquakes identification. Scientists have recently deployed fiber optics in boreholes with sensors to measure temperature, strain, and seismology, allowing for continuous temporal and spatial data. The Monterey Accelerated Research Center, located at USA, sponsored a recent application in marine geophysics that recorded a mild earthquake and discovered many undersea fault zones. This equipment can give quite fast results as it allows researchers to map an unknown fault system and detect various dynamic events in the water column above just within a few days. The last method used is seismic imaging. Most marine geohazard investigations are based on seismic imaging, which gives the most reliable information for analyzing the geology beneath the seafloor. Seismic methods that look 5 km below the seafloor can resolve geological features of roughly 50 meters, yet seismic methods that just view the top 25 meters can resolve geological features of up to 25 centimeters. Modern systems can create three-dimensional images of the subsurface. This modern technology can give the ability to identify and expose the major tectonic structures, such as tectonic faults along which earthquakes occur and landslide deposits, which reveal which areas of the continental edges are unstable and how frequently landslides occur in a certain place.
Next, the feature of seafloor mapping. As we all understand, the seafloor and associated processes are closely linked to its bathymetry. Mapping the gaps in the world's oceans will not only better our knowledge of the seafloor but the oceans in general. This knowledge is a significant contribution to the development of sustainable ocean management plans and allows us to respond appropriately to modern challenges such as environmental degradation in the marine realm, climate change, geohazards, and a growing ocean industry. It is clear that mapping the world's ocean is not a task that can be tackled by one sector or project alone. Hence, collaboration and coordination across sectors sectors and at a variety of scales is needed. Seabed 2030 is a project born of this recognition as presented at the Forum for Future Ocean Floor Mapping held in Monaco in June 2016. The success of future mapping efforts will be reliant on the continuation of these existing efforts and appropriate mapping strategies to provide ever-increasing volumes of high-quality data from throughout the global oceans, increasing the flow of existing and new high-quality data through the IHO DCDB and other recognized data centers from across the marine community, including the international research community, the commercial sector, and via crowdsourcing programs, will provide a huge boost to the data availability. In sum, an increase in data gathering activities combined with effective targeting of future mapping programs and latest technology developments, as well as efficient data processing chains and mapping expertise will be needed if we are ever to deliver knowledge of the seafloor comparable to our knowledge of the land surface. Promotion of collaboration and transparency among all sectors would further develop open access data policies for all sectors. We can have a continuous incorporation of updated bathymetric information into ocean management plans to promote technology developments regarding enhanced data quality, but also address the needs of low-budget user group by developing low-budget solutions.
In conclusion, seafloor geohazards, namely earthquakes, are one of the major concerns worldwide. Assessment of seafloor geohazards involved several communities facing different interests and needs. Technological development is offering marine geology a powerful seafloor mapping tools, multi-beam bathymetric, and above all, they are essential for geohazard characterization, and through repetitive surveys, monitoring and understanding of ongoing geological processes, high-resolution seafloor mapping does not only enhance the assessment of marine geohazard, but it is also a booster for the scientific knowledge on seafloor tectonics, erosional and depositional processes. The study of geohazard-bearing features provides an opportunity for collaborative activities between academia, industry, as well as public authorities in charge of land planning and civil defense. However, for the different communities, geohazard assessment have different objectives, time span and required precision in forecast. Regardless of the different approach, seafloor mapping remains the unavoidable, if not the main step in the geohazard, namely earthquake assessment process. That is it from us, Carbino Forest Group. Thank you for lending your ears and have a good day.